Hi structural engineers, welcome to the structural engineering lectures and welcome to the new playlist on analysis and design of structures using STAAD.Pro, E-tabs, Excel spreadsheets, seismic and wind analysis. Right? In today's class we shall discuss analysis and design of RCC circular beam or ring girder using STAAD.Pro and verification with manual calculations. Right? Now we will be discussing this as per the limit state of reinforced concrete structures conforming to the codes IS 456 Indian Standard Code of Practice for Plain and Reinforced Concrete and SP 16 1980 Design Aids for Reinforced Concrete to IS 456 as well as IS 4995 Part 2 1974 Indian Standard Code Criteria for Design of Reinforced Concrete Bins for Storage of Granular and Powdery Materials Part 2 Design Criteria. Whereas in the previous class we have discussed analysis and design of continuous steel beam using STAAD.Pro, verification with manual calculations, conforming to limit state method IS 800 2007 student. I hope you enjoyed the discussions there. Now, if you enjoyed, you just try to click like, share, comment and subscribe to our YouTube channel. Now let us move to the discussions. Before we move to the discussions, let us see the brief biodata of me, the speaker, right? I, Dr. D. Rupesh Kumar, obtained my BTech Civil Engineering from Nagarjuna University in 1984 and MTech Structural Engineering from JNTU Hyderabad in 2000 and PhD Structural Engineering from JNTU Hyderabad in 2009. Presently, I am working as Associate Professor in Civil Engineering Department, University College of Engineering, Osman University, Hyderabad, Telangana State, right? I have an experience of 27 years, of which 7 years is in industry and 20 years is in teaching and research at graduate, postgraduate levels, right? My research areas include the reinforced cement, concrete, steel designs, structural analysis, finite element analysis, earthquake engineering, bridge engineering, structural optimization, right? I have published 45 research papers in international national journals as well as conferences and organized 3 international conferences and 11 national conferences workshops and attended 43 workshops and visited 2 countries, right? And delivered 13 guest lectures and edited 3 books and supervising 14 PhD scholars and supervised 30 ME theses. I am a member of various professional bodies in India and technical committees for inspections, right? I am actively involved in various consultancy works that are offered by the department and completed over 750 design proof checks and 150 design of RCC steel composite buildings and high-rise towers and rail as well as road bridges, etc. Right? Presently, I am an executive council member of Indian Concrete Institute, Hyderabad. Right? This is a brief profile of mine, that is a speaker. Right? Now let us move to the discussions today. This is how. Now we'll move to the discussion wherein we'll see what is analysis and design of RCC circular curved beam. Generally, these curved beams will be there for the deep bins, right, which are called the silos, right? At the bottom of the silos, these bins will be there, right? Like this for silos at the bottom, curved beams, right? Are for the water tanks, right? The circular ring girder beam, right? Like this circular ring girder beam, right? And for how to analyze this as per this IS 456 2000, which is the RCC code. Now we'll discuss in today's class, right? As well as we'll see the manual calculation followed by the modeling the same in the STAAD, right? Then we'll compare the one result with that of the other, right? And we'll see what is the percentage error in both of these, right? Now let us say the problem definition, student. This is how the design and detail a circular beam for a water tank supported on 4 equally spaced columns on 5 meter diameter, right? Curve subjected to a UDL of 14 kilonewton per meter, use M25 grade concrete and Fe 500 grade steel, use shear force, bending moment and torsional coefficients as per the code 4995 part 2, right? That is what the data given, student. And now just make note of what is the data given, student, right? The radius of, because the diameter is given for this circular girder, that is equal to 5 meter, therefore radius is equal to 5 divided by 2, 2.5 meter, and UDL is given as a total live load, right? Total live load is 14 kilonewton per meter, and the number of columns is 4 numbers is given. And I'll just go to this IS. I'm there in IS 4995 part 2 1974, which is the Indian standard criteria for design of reinforced concrete beams for storage of granular and powdery material, student, right? Wherein now I have to have these coefficients. I'm just making note of the coefficients from this, right? One moment, right? From table 3, I have to have for 4 number of columns, right? I have to have the maximum shear force WR divided by 8, right? And K1 0.0342, K2 0.0176, K3 is equal to 0.0053, and the maximum torque occurs at 19 degree 12 minutes. Therefore this data I am just making note of, right? Here I have just noted down that data from IS 4995. This data I have just noted from IS 4995. And what is also given is FCK, the characteristic compressive strength of the concrete 25, and yield stress of the steel is given as actually it is 550, student, right? It is given as 550, right? I'm just making note of that as 550, right? Not 500, student, right? Because later on I am using only 550, right? Therefore if it is not 500, I am just using 550, right? And nowadays, right, 550 grade is easily available in the market, right, compared to that of the IS 415, right? And now to start with, I am assuming the section. Now these are my assumptions, that I am assuming the width of the beam as 230 and the depth of the beam as 300, with a cover to the reinforcement as 25 mm. These are my assumptions. If these are my assumptions, then what I'll do is I'll just first calculate the loads. However, what is now given in the problem is that load is a superimposed load. Therefore, that was a live load only. Now I'll add the dead load to it. Right? Therefore, what is the dead load? The self weight of the beam is with this assumption 0.3 multiplied by 0.23 multiplied by unit weight of this concrete from IS 875 part 1. The density of the concrete from IS 875 part 1. I have to have 25 kilonewton per meter cube. Therefore, for 1 meter length, I'll calculate. That now works out say 1.725 kilonewton per meter. And whereas already the live load WL, this is WD, whereas WL or WS is given as 14 kilonewton per meter. Therefore, the total load W is equal to 15.725 kilonewton per meter. Right? Here, no information is given. Therefore, I am assuming that these are the service loads. Right? Therefore, now I'll multiply with the partial safety factor of 1.5 to get the design load. Right? 1.5 multiplied by dead load plus 1.5 multiplied by live load. Therefore, 1.5 multiplied by 15.725 now gets 23.587, student. Therefore, now the total load on the ring beam or the circular beam is equal to capital W is 2 pi r. 2 pi r is the total peripheral length of this beam multiplied by W. Therefore, that design load is 23.587. Therefore, if I just multiply now, I'll get say 370.51 is the total load on the ring beam. The total load on this ring beam is equal to 370.51, student. Right? Now, once on this ring beam, right, like this, right? Therefore, once I get this 370.51 load, then what I'll do is I'll move to the bending moments and shear force coefficients, right? This is how the ring beam, student. What now I'm showing is a ring beam. a ring beam, right? Now this is up, right? Therefore, now let me move to the top. The once I get the loads, now I'll calculate the design forces. Therefore, the maximum negative bending moment at the support as per these questions which I just made note of from IS 4995 part 2, 4995 part 2, right? This is out from IS, either IS 4995 part 2 1974 from that table 3 just now we have seen, which is as applicable to RCC bins, or alternatively what you can do is that you can also refer IS 9178 part 2 1979 table 3 page number 37, which is applicable to steel bins, steel deep bins, right? For further knowledge about the designs of the steel bunkers and silos, please refer back to our playlist on advanced steel designs. There you see the designs of bunkers and silos conforming to this IS 9178, right? Elaborately, student, right? That is only for your benefit of doubt. I am giving this information to you, right, for additional information, right? Therefore, the maximum negative bending moment at support is now K1WR. K1 is just now noted from that IS 4995. Therefore, that is 0.0342 multiplied by the total load 370.51 multiplied by R. Radius is equal to 2.5. Now it works out. That divided by now all these are in terms of kilonewton meter. My working units are kilonewton meter. Therefore, now I'll get 31.67 kilonewton meter. Similarly, the maximum positive bending moment at midspan is equal to K2WR, where K2 is the positive bending moment coefficient, whereas K1 is the negative bending moment coefficient at support from IS 4995. Just that we already noted down as K2 is equal to 0.0176. Therefore, substituting these, now I'll get that maximum positive bending moment at the midspan as 16.3 kilonewton meter, right? Likewise, the maximum twisting moment or torque at an angle of 19 degrees 12 minutes, just now we have seen, is given by T or MT is equal to K3WR, where K3 is the bending moment, the coefficient for torsion. K3 is equal to 0.0053. Therefore, multiplying with W multiplied by R, now I'll get 4.909 kilonewton meter. Whereas now I'll have the total the shear force at the support reactions at the support reaction. What is the shear force is now given by WR theta divided by 2. Therefore, W is equal to factored load 23.587 multiplied by R. R is equal to 2.5 multiplied by theta. However, I do have columns at every 90. Therefore, 90 multiplied by 4, 360, because the girder is supported on 4 columns like this, right? Therefore, I do have theta is equal to 90 degree between the two columns, right? Therefore, that divided by 2, it now works out 46.32. Whereas the shear force at a section of maximum torsion, now it works out 46.32 minus this 23 point. I'll just interpolate because it is for 90 degree. Therefore, for 19 degrees 12 minutes means 19.4 degrees. It is how much, right? How much is the reduction? Therefore, I'll reduce by this much of amount. Therefore, after interpolation, now I'll get the shear force at the section of the maximum torsion as 20.64. I hope students understood the analysis of this circular beam. This circular beam subjected to the load. Now let us visit to that of the analysis. First, we'll see the analysis in STAAD, right? Now, let us move quickly to that of the STAAD. Therefore, I'm there in the STAAD model, student. I'm there in the first page, which is called the setup page. I'm there within that job page, right? Therefore, this is my circular beam, RCC circular beam. Therefore, I am having this, and I am saying that this is STAAD2, right? and I'm noting down the file name and directory where it need to be saved, and when, on which date it is generated, and it is created by which engineer and checked by which engineer, as well as approved by which engineer, right, on which date, that is also given, right. Therefore, using this information now I'll go to the next page as that of the geometry. Now I'll define all the nodes. Right. That is how my first node, student. Just a moment, right. Therefore, I'll define all these nodes, right. Node number 1, node number 2, node number 3, so on and so forth, right. Right. Now, that is how I'm defining all these nodes, right. Node number 1, right, which is there at 2.5 x 2.5, y 0, y in the STAAD, y is in the vertical direction 0, and z, right, z, this is x, y, z in the STAAD, right, x, y, z, that is how, right, x, y, z, you rotate in the counterclockwise direction. Therefore, z is equal to 0, like that. I do have the second node, and likewise now I'll move to sixth node, right. Now it is there at x is equal to 0, y is equal to 0, and z is equal to minus 2.5. Now similarly I move to the top of the 11th node, which is created at minus 2.5x, and y is equal to 0 and z is equal to 0. Likewise now I'll move to the top of the 16th node, x is equal to 0, y is equal to 0, and z is equal to 2.5, and last is the top of the first node itself. Therefore, that is how almost a 360 degree all the 20 nodes I have defined, right. Therefore, once I define this, now what I'll do is I'll define what are the previous case just now I have defined in FEM finite element method. I have defined nodes. The next step I will define the element connectivity table, right. Therefore, in that element connectivity table, we will establish the relation between the local and global correspondence of the degrees of freedoms, right. Therefore, now my first beam is connected between the node number 1 and 2. Let me just switch on the beam number, students, right. This is just turning off the beam numbers. Therefore, this first beam is connected between the node number 1 and 2. Second beam is connected between the node number 2 and 3, so on and so forth. The last one, 20th beam is connected between the node. The first node is local first is global 20, local second is global 1. That is how the element connectivity table will establish the relation between the local and global degrees of freedoms, right. I hope you are understanding this discussion. Once I conclude this geometry, definition of the geometry, student, now what I do is I don't require these parameters, etc., right. Therefore, now I will go to the general page. This you already just seen that we have assumed this beam as a rectangular cross section with 0.3 depth, 0.3 as the depth, and 0.3 as the overall depth, and 0.23 as the width. Therefore, that is how this is a cross section at any given location, right. This is what my circular beam. Now you can see that between one node to one node, it is modeled as a straight beam, right. Now please make note that this is just modeled as a straight beam, though it seems as if a curved beam, right. Actually, the STAAD will do by, in the absence of data, if you give beam connectivity, it will connect by straight beams only. In the second part of this, we will also see if it is modeled using curved beam, how the analysis is going to be affected. That we'll see, right. Therefore, I don't have any other specifications. Then let me move to the top the specifications. I don't have any specifications, student. Then I'll move to the supports, right. Supports. Therefore, these are my 4 supports, which are fixed supports, right, at node number 1, at node number 6, node number 11, node number 16. I do have the 4 fixed supports. Then once I do that, I don't have any other definitions rather than that of the dead load and live load. Therefore, I don't have even vehicle time history or wind, seismic, etc. Therefore, I'll just skip off that page, student, right. Now I'll directly go to that of the definitions of the loads, right, like this, right, which is the first one is the dead load as well as live load, right. Therefore, this is my dead load. Now Once I click this sulfate y minus 1, I am having this red, right? All the members are assigned with that sulfate acting in the downward direction. Y in the downward direction is negative, whereas y in the upward direction is positive. Therefore, y minus 1. Whereas this is that of the live load, student, right? Live load is 14 kilonewton per meter, 14 kilonewton per meter, right? Now these are unfactored loads. Therefore, now what I'll do is in the next subheading, now I'll define the combination of these loads, right? 1.5 multiplied by dead load plus 1.5 multiplied by live load, right? Once I define these loads and load envelopes, student, now what I'll do is I'll define the materials, right? This is what my concrete material with the relevant properties of this concrete material, right? What is the Young's modulus, what is the Poisson's ratio, etc. are now defined, right? Therefore, once I define this one, right? Now I'll move to the next page. Right? I'm just moving page by page. Now I'll move to the analysis page, student, right? Analysis page. Therefore, once I perform analysis, now I'll say okay, run analysis. Now you can see just I'm clicking, right? Therefore, after clicking, I'm just getting the output only just in 1 second. That is the advantage of using the STAAD. Just within one second only I got the output. Now I'm checking for adequacy as well as the failure of the members. I don't have any failed or these members. Therefore, now directly move to the top the concrete designs. However, before I move to the concrete design, student, let me just go back because now I need to do the designs because I have just analyzed. Therefore, I'm there in the last page, which is the design page, student, right? Before I do analysis, I forgot that. Therefore, I'm there in concrete designs, whereas I've just clicked IS 456 2000, which is the limited code, right? And I'm saying that this is the Indian code, right? And the clear cover to all the beam members as per this IS 456 is 25 mm, and I'm saying that these are the other properties, right? FCK is equal to 25 Newton per mm square, and Fi for the main steel is 550 Newton per mm square, and for the secondary steel Fy yield stress is equal to 450 Newton per mm square. The maximum main diameter of the bar is 12 mm, and that of the secondary beams is only 8 mm. And torsion zero means you take into account the torsional effects as per the IS 456, right? And now I'm saying design the beams and take concrete quantity as well as end the beam. Once I do this, now I'm just clicking analysis. Therefore, in 1 second I got the analysis, and I already checked that there are no failures of the beams. Therefore, this is how my design. Now the designs are seen. Therefore, how much of top reinforcement is required at the first beam? That is for the negative steel 318, slowly varying to up to the 782 mm. 107 at the bottom I don't require, right? Like that 318 is the maximum negative steel, student, right? Whereas now I'll go to the second beam 122, bottom steel 122, like that, right? This is the maximum value 122. Positive steel is only 122. Therefore, I got these outputs. Even you can see in the beam 4 at the bottom I am getting only 122. Therefore, I'll just note down these relevant values, right, of the steel. As well as you can see the shear reinforcement 8 dia, 2-legged 8 dia at 110 center to center. And how many number of rods should be provided? Here it is saying 10 number of rods, because 10 mm is approximately 79.5. That means 80, approximately 80 multiplied by 6. It is saying okay 480, but we can provide using 12 mm dia bars, right? Say 3 multiplied by 113, say 339. If I provide 339 as the negative steel, right, or the steel at the top, that is sufficient for me. Whereas the bottom steel I am getting only just 123. 123 is my maximum steel. Therefore, even if I just use only one 12 mm dia bar, it is not sufficient. Therefore, the number of rods of the 12 mm diameter required are, say, 122 divided by 113, 1 point odd value. However, in any case, not less than two number of bars, not less than two number of bars. Therefore, let us use two bottom steel as the two 12 mm dia bars, right? Once I examine this, now let us move to the top. There, I'll go to the next page, student, right? And there now post processing. I'm moving to the post processing page, right? Wherein I do have the post processing results. Post processing results are available, right? Now I go to the beam graphs, right? Beam graphs, I am seeing that, right? Therefore, I do have the output, right? For the first beam, I am having the maximum movement. Maximum movement is varying from 33.7 to 4.8. Now let us see this as per the manual calculations. As per the manual calculation, right? Now what we got? I'm just revisiting back to the top the manual calculation, student. Now what I am seeing from the STAAD, is the minus 33.66, whereas using this IS 4995 coefficients, I obtained that output as the maximum negative bending moment as 31.67, but STAAD is giving that output as a value the 33.67, hardly there is 6% error, means STAAD is giving 6% more result if it is modeled as a straight beam. Later on we will also see if it is modeled as a curved beam, then the output is equal to 33.85. There is a small change, hardly there is a small change, but we'll see, right? Likewise now I'll see what is the maximum positive movement. From this STAAD, student, right? This is how it is varying from 33.3 to 4.8, 33 right? Even I'll go to the second beam, right? Therefore, for the second beam, it is varying from 3.94 to the top the 10.15, whereas in the third beam I am getting, yes, the maximum negative movement is varying from minus 11 to minus 11, but at a distance of 0.395 starting from the node 3, I am having a maximum negative bending moment of 12.28. Therefore, I'll just make note of that and I'll compare with that of the manual calculations as per IS 4995, student. But here the STAAD is giving 12.84, whereas with the manual calculations I got 16.83. That here the STAAD is giving almost here and there 21.5% less result, right? 21.5 is a less result, right? Like this, right? It is 21.5 is a less, right? Likewise, now I'll compare this torsion what I got from manual calculation 4.91 kilonewton meter, whereas let me check in the STAAD. What is that output, right? In the STAAD I am getting this output. Now you can see in the modeling and there in the output, student, right? Now we can see, right? For checking that torsion, I need to go to the other page. It will not be shown in the graphs, because in the graphs only MZ, Fy and Fx will be seen. Now just let me check first the shear force, then I'll go to that page, student. Just wait for a moment, right? Let me check, I'll come to that, right? Therefore here I do have the shear force at the support from manual calculation as 46.38, but STAAD is giving 46.1, which is 0.5% less. Now let us show that, right? 46.1, how? Like this, right? Here you can see here at the first support I do have the output as 46.1, slowly varying at the second node as 27.7 to 9.22, right? 9.22 to the other side, minus 9.22, student, right? Later on that minus 9.22 to minus 27.7, right? That is how minus 27.7 to minus 46. You please see that at node 1 it was plus 46.1, whereas the support is there at the next support, right? Therefore there is a sixth node, at that I do have a support. Therefore it is varying from minus 46 to plus 46, right? Whereas at the support 1 it was 46.1. Therefore linearly varying from minus 46.1 to plus plus 46.1 plus 46.1. That is how the variation of the shear force. Similarly, you can see at the last node 7, still I do have a maximum bending moment of 33.7. even that was seen here also, right? The same will also be seen at the last beam at the last end, same 33.7. That is how the shear force is noted down, student. I hope you are understanding these discussions, right? I've just noted down that from the start 46.1. Therefore I've just noted down, and let me calculate this shear force at the section of maximum torsion, right? At the maximum torsion, right? I need to calculate manually, right? Here from the STAAD, it is 22.66. how I am just calculating, right? Whereas just now we have seen that the bending moment per unit length, it is varying from 3.94 plus 10.5 over a chordal length of 0.78217. Therefore that variation of that bending moment is 18.46 kilonewton per meter. Whereas I do have point of counterflexure is at 3.94 divided by 18.46. 3.94 divided by 18.46 means point of counterflexure will occur at a distance of 0.2134 from the node number 2, at a distance of 0.2134 from node number 2, right? Therefore at this much of distance, actually starting from the node number 1, because that first member is of the distance point, its length is equal to 0.7821. if I add to that, therefore from the left support or the column support, it is at a distance of 0.996 meters approximately, right? Therefore what is the shear force variation per unit length? It is now, just now we have seen the variation 27.7 is decreasing to 9.22. therefore it is decreasing over a length of 0.7821. therefore that change of shear force per unit length is 23.63 kilonewton per meter. Therefore the shear force drop at a distance of 0.2134 meter is equal to how much? It works out, say, upon interpolation 22.62 plus multiplied by 0.2134, it is 5.04 kilonewton is the drop. Therefore the shear force at this point of counterflexure 0.2134 is equal to how much? Therefore the shear force at that location is equal to 27.7 minus this 5.04, it works out 22.65 or 66. However using manual calculation I got 20.64, whereas from the start I am getting 22.66. The start will not directly give this value, student. I have just interpolated, right? Now once I see this, let me check this the shear force at this already seen, right? Let us check this torsion value, where I am getting this 3.41. For that, now what I'll do is, instead of graphs, I'll go to the the forces, student. Now I am there in the this page. Therefore I can see that I do have the summary. I am there in the summary page, student. Now you can see that I do have the maximum results are seen. Right here. Therefore now you can see that mx is maximum in beam 9, which is 3.409, right? Just now we have seen that the maximum negative bending moment is occurring in the beam 1, 33.66. Also in the same beam we do have maximum shear force of 46.12 kilonewton. Therefore this is how this gives the summary where it is happening, right? And the maximum torsion is happening in this beam number 9, right, which is 3.409. I'll just note down that, and I'll go to that the force diagram, right? That is how the force diagram, student. I am there in this force diagram, where now I'll just turn on view values. Therefore now I'll say okay, you see, let us see the maximum values, right? Maximum values. Now it is displaying the maximum values, right? That is how the maximum bending moment at the support 33.6, right? Like that, right? Even at this second support the same value, or third support same value, and fourth support you can see the same values are seen, right? That is how. Even where we do have that positive bending moment, right? Positive bending moment is equal to 12.83. This value you can see, right? It is varying from that to minus 10 positive, right? Whereas maximum positive is equal to 12.84 minus, right? This minus means positive actually, right? Positive bending moment or sagging bending moment is equal to 12.84, whereas maximum hogging bending moment at the support is equal to 33.6 hogging bending moment, whereas sagging bending moment maximum value is equal to 12.84. Therefore this is how I'll note down from this one, as well as you can see the outputs even for the shear also, student, right? Like this. Let me go to the shear diagrams, right? Shear diagrams. Therefore I have to have the maximum shear forces, right? That is how the maximum shear forces are now shown, right? Now I have to have maximum shear force at the support 46.124 kilonewton, right? Slowly varying to 27 to 9.26, right? Like that, right? Whereas this positive value of 46.124 is linearly varying to the next support at the support 6 as minus 46.124. Further it is increasing, it is moving to the upward, right, by 46 point, this one, right, to the next support minus 46, right? Like this, minus 46 to plus 46, minus 46 to plus 46. That is how the variation of the shear force diagram, student. I hope you understood. Like that, even now you can see the other results, right? Whereas if I go to the other results cannot be displayed here. Only these bending moment and shear force can only be displayed, right? Whereas even you can see the axial forces, right? Therefore for which I need to activate these axial forces, this, right? Therefore these are my there are no axial forces. I don't have that, right? Even you can see the maximum deformations, right? Maximum deformations also, like this, right? Let us see the maximum displacements, right? What are these, right? Right, these are the maximum displacement values, right? Even that can also be seen, now I do have all these outputs. Therefore now let me go to that of the design page, right? Therefore I hope you understood this discussion, student, right? Once I obtain these results and compared one with the other, therefore now I'll finally take the design moments, right? What is my design moment? From manual calculation I have to have 31.67 and positive bending moment is equal to 16.3 and torsion is equal to 4.909, whereas compared to that of the STAAD it is 3.41, just now I have shown, which is 30.5% less if it is modeled as a straight beam, whereas if it is modeled as a curved beam then I am getting 2.22. If it is modeled as a curved beam then I am getting that result as just 2.22 only, the torsion, right? And this is my shear force 46.32 and the shear force at the section of the maximum torsion 20.64. Therefore using this, now let me just initiate the manual calculations of the designs. Yes, student, I hope you are understanding the discussions. Once I conclude the analysis using manual calculations as well as that of the STAAD, now let me just move to the manual calculations of the designs of this reinforced concrete circular beam, right? This is already discussed at graduate level, student. Therefore I will now move at a quicker pace, right? Design of the RCC beam, right, subjected to a design bending moment of M 31.67, just now we have seen that, right? 31.67 and 46.32 shear force, 46.32, this one, right, from manual calculations, right? Whereas we already know that for Fe 550 grade steel from IS 456 class 38.1 page number 70, one moment, student, right? Page number 70 IS, this one, right? Page number 70 means this page, right? This page, I'm there in IS 456, right? Therefore I do have for FI 250, 415, 500 XU max by D, right? These values are given. For 550 is not available. Therefore now what I'll do, I'll just calculate. I'll calculate from fundamentals using this fundamentals of. Let me also revisit to this design aids for reinforced concrete to IS 456, which is SP. This is what, right? Design aids for concrete for reinforced concrete, which is IS 456 1978, which is called the SP16, right? Therefore this SP16 1980 student. Now I'll quickly move to the top, the flexural members side. I am there in the flexural members page, right? Therefore here in flexural members I do have all the formulae are given, right? Therefore this is how you can calculate XU max by D using this formula 0.0035 divided by 0.0055 plus 0.87 Fi divided by ES, right? Substituting which here the values for XU max by D are given up to 500 only. Therefore now you substitute 550. Therefore now you can get upon substitution, you can do on your own, student, right? You can check on your own that it works out 443. Therefore once I get this, now I'll also check what is MU limiting value. Then I will go to IS 456 page number 96, student. Just one moment, right? IS 456 page number 96. I'm just going to that, right? And then in that same page, right, movements of resistance of rectangular and T sections, annex G. Therefore here I do have MU limb given by this. MU limb is given by this, right? Whereas if XU by D is equal to the limiting value R, right, then MU limb is given by 0.36 XU max by D 1 minus 0.42 XU max by D FCK BD square, right? Therefore where XU by D is given by this formula 0.87 Fi AST divided by 0.36 FCK BD, just now we have seen. Using that only we have just obtained XU max by D, right? Whereas this is MU formula, student, which you are already aware of. MU is given by this sigma st multiplied by AST multiplied by lever arm. Therefore sigma st is equal to 0.87 multiplied by Fi multiplied by AST. That lever arm is equal to this D taken outside, D multiplied by 1 minus Fi AST divided by FCK BD, right? These are the formulae which you are already aware of, right? Therefore using this class G 1.1 C, this is MU limb. Now I will calculate MU limb, student, right? Or alternatively the same is also given in SP16 like this, right? Therefore for different using that same formula for the 3 grades of the steel, these are given for 250.14 for 415.138 for 500.133, whereas for 550 it is not available. Therefore now I'll just substitute in that and I'll check that it works out 0.129 FCK BD square. Therefore once I know that, therefore what's the depth of the beam required is square root of MU divided by 0.129 FCK B. Now whereas I have to have FCK is equal to 25 and B, breadth of this beam is equal to 230 and MU, the factored bending moment, is equal to negative bending moment at the support, right? There is a hogging bending moment 31.67. Therefore if I substitute that, now I will get say 206.63 is the depth required from flexure point of view, at the support. However, what is the depth provided? Depth provided is equal to 300 minus 25 minus assuming 12 mm dia, right? Right? Now I have to have 300 minus 25 minus 6. Therefore the depth provided is equal to 269. Therefore it is okay, right? And there is one comment, right? And the depth required from flexure point of view is 206, whereas that provided is equal to 269 or say 265 as appropriate, right? 269 I am saying, right? Therefore the second comment, the second inference is that the section is under reinforced. Means concrete will reach its permissible stresses first rather than that of the steel reaching the permissible stresses first at the bottom, right? Therefore concrete will reach the permissible stresses, right? Hence this unreinforced section, hence now I'm saying that now I'm saying effective depth is equal to start with, I'm saying effective depth is equal to 300 minus 25, right? I'm assuming that 25 itself has the effective depth rather than that of the clear cover, right? Actually that 25 should be the clear cover to the beams, right? In calculation I'm taking that as the effective cover, student, right? You can do the change in calculations whatever that, but there are small changes, right? Therefore that effective depth is equal to 275 rather than that of the actual effective depth is equal to 269, right? Therefore now using this formula, just now we have seen IS 456 that M is equal to 0.87 FIST multiplied by 1 minus FIST divided by FCK BD, right? This gives a quadratic equation, solving which what is AST is unknown, or the same AST can also be written using this formula. AST is equal to 0.5 FCK divided by FI multiplied by 1 minus square root of 1 minus 4.6 mu divided by FCK 4.6 mu divided by FCK BD square multiplied by BD. Either of the two will give, substituting the numeric values 0.5 FCK 25 and FI to 550 and mu is equal to 31.67 kilonewton meter means 10 to the power 6 Newton mm. Now I am substituting everything in terms of Newton mm, FCK 25 and B is equal to 230 and D effective depth 275 rather than that of 269, right? Even now you can substitute 269 if you wish, assuming the clear cover as 25, right? That multiplied by BD 230 multiplied by 275. Now I require area of the steel at that support is equal to 265 approximately, but we already seen just now from the analysis and design, even we have concluded the designs using the STAAD. There I got from the STAAD 318 mm square, 18 mm square, almost here and there, right? 318 minus 265 divided by 265, almost it is just 20% more, right? Now let us see what the code says for the minimum tension steel as per this class. IS 456 class. I do have this given by A naught by BD multiplied by is equal to 0.85 divided by FI, right? Therefore this is from IS 456, student, right? IS 456, I have just recall that, right? From this page, right? Therefore substituting which, now I'll get the result, sorry, this page, right? Not this page, student, right? Therefore AST divided by BD, right? From this class number 26.5.1.1 26.5.1.1, right? The minimum tension steel is given by AST divided by BD is equal to 0.85 divided by FI, right? From this class 26 5.1.1 page number 46. Therefore from that now let me substitute now and check what is the minimum area of the steel. Therefore substituting the numeric values, I'll get approximately minimum steel required is equal to 98. However from flexure point of view I got 266 approximately. Therefore 266 is greater than 98. Therefore this will govern. Let us say if I got this result from bending point of view 65, approximately 65, but that value should not be less than 97. Therefore that AST minimum will govern the design, right? Therefore now 265 is governing the design. Therefore for 265, assuming if I assume 10 mm dia, that divided by approximately 80, but 10 mm dia should not be used as the main steel in the beams. Just bare minimum steel diameter of the steel that should be used is 12 mm. Therefore 12 mm diameter will have 113 mm square. Therefore number of rods required, n is equal to 265 divided by 113. Now I require divided by 113. Now I require 2.34 number of rods, but to the next integer 3. Therefore 3 multiplied by 113, say 339. AST provided is equal to 339 against required is equal to 265. Therefore okay. Now I'll show that schematically, right? Once I do that, now next subheading is check for shear. Therefore the nominal shear stress is given by this VU divided by BD, where VU is a factor of shear force 46.32 10 to the power 3 newtons divided by BD 230 multiplied by 275. Our actual value is equal to 269, right? Now I'll get nominal shear stress as 0.732 Newton per mm square, whereas I already provided a steel of 3 multiplied by 113, a steel of 339. Therefore what is the percentage of steel? I can calculate AST 100 AST divided by BD. Now it works out, say approximately 0.496, right? Therefore for that, now I'll go to this table 19 of IS 456 from page number 73. From page number 73. Therefore I'll go to page number 73, student, just a moment, right? 73 means, right, I'm there in this page number 73, right, which is table 19, design shear strength of the concrete, right? Therefore for 100 ST by BD 0.5, for M25 grade this is approximately 0.49, whereas now you can interpolate for 0.25 it is 0.36. Therefore for 0.496 it is how much? The design shear strength of the concrete tau c is equal to how much? Therefore that is how you can do. Even for the from table 20 you can see the maximum shear strength tau c for M25 grade concrete is equal to 3.1. Therefore I do have these two inputs. Therefore now I'll recall that upon interpolation I am getting tau c design shear strength is approximately 0.49 Newton per mm square, whereas I do have a nominal shear stress of 0.732. Therefore what 0.732 is much greater than the shear design shear strength of 0.49, but however that is much less than the the permissible maximum shear stress of 3.1, permissible shear stress of 3.1. Therefore it indicates that the grade of the concrete need not be upgraded. Using the same M25 grade you can manage the designs further, right? But because tau v is greater than tau c, now I need to design for the shear reinforcement as per this table 73. Just now we have concluded. Therefore the shear carried by the stirrups is given by VUS is equal to VU minus tau c BD, where tau c BD is the shear carried by the pure concrete alone, right? Therefore total ultimate shear minus shear carried by the concrete alone excluding shear, excluding the steel. Therefore that now works out for the stirrups I need to provide VUS is equal to 46.32 minus 0.49. Just now we have seen that permissible value is equal to 0.49 multiplied by 230 multiplied by 275 is equal to 15.32. The reinforcement carried by the stirrups is equal to 15.32. However, this should not be greater than half that value VU, right? However, half that value means 23.16. 15.32 is much less than 23.16. Therefore it is okay. If it is, let us say, some you are getting some 25.32, that is not acceptable. You just restrict it to 23.12 only, right? 23.12 only, right? That is how. Whereas we need to provide in other format, right? Therefore now let us see this. What should the spacing? Now I am assuming the vertical stirrups, right? Therefore as per this IS 456 class 40.4 page number 73, the spacing of these vertical stirrups is given by this, right? Therefore shear reinforcement shall be provided to carry a shear of VU minus tau c BD. Using these vertical stirrups, VUS is equal to 0.87 FI ASVD divided by SV. However, the code says that FI in any case should not be greater than 415, right? Therefore substituting is now I'll get Here I am assuming 8 mm dia 2 legged stirrups, 8 mm dia 2 legged stirrups, therefore of FE 415 grade steel student. Therefore the area of the 2 legged stirrups is equal to 2 multiplied by pi by 4 8 square. This is 2 multiplied by approximately 50 100 mm square, because 8 mm dia will furnish approximately 50 mm square, multiplied by 2 means 100. Therefore that is how ASV multiplied by D is equal to 275 and 0.87 multiplied by 415 divided by VUS is equal to 15.32 kilonewton 10 to the power 3, right? Therefore that gives the spacing required to resist this 15.32 kilonewton is 651 mm. That is too large value. However, the code says that there are the upper bounds for the spacing also as per this IS 456 class 26.5.1.5 page number 47. Now I'll just quickly move to that page number 47, student, right? Therefore page number 47 I'm just moving to that page number 47, student, right? Therefore there I do have this upper bound value, right? Maximum reinforcement, not that one, right? Maximum spacing for shear reinforcement in the members shall not exceed 0.75 D for vertical stirrups, whereas for the inclined stirrups, it should which are inclined at 45 degree, the maximum spacing should be D, right? Now we are there in vertical stirrups, therefore it should not be greater than 0.75 R, and upper bound value in any case the value should not be exceeding 300 mm, right? That is how. And even we do have the minimum shear reinforcement criteria also given by this, right? Minimum shear reinforcement in the form of the stirrups should not be less than ASV divided by BSV greater than or equal to 0.4 divided by 0.85 FY divided by right 0.87 0.4 divided by 0.87 FY. Therefore I'll check these two criteria also, right? Now first of all let us check, right, from minimum shear reinforcement criteria point of view. Therefore if I go to that, because I am getting too large value, 8 mm 2 legged stirrups, 261 is too large. Therefore how much is required from minimum shear reinforcement criteria point of view given by that just now we have seen that code specification, right? Therefore SV, if I substitute that, now I'll get SV should be less than or equal to, upon substitution, 2 multiplied by the 50.2, this is ASV, right, multiplied by 0.87 multiplied by FI 415 divided by 0.4 multiplied by 230 is the 230 is the breadth. Therefore now I'll get 394. Therefore the spacing should be less than or equal to 394 from minimum shear reinforcement point of view. But from design point of view I got 651. That indicates that the design shear reinforcement is not governing the design of the shear, but only the nominal shear reinforcement or just now we have calculated from this is governing the design. But however even the third the upper bound values are there from this, that for vertical stirrups the maximum spacing should not be more than 0.75 multiplied by D. Now it works out 206, or that even in any case this 206.25 should not be greater than 300. Therefore 206 is not greater than 300, therefore okay. But however even that minimum shear reinforcement point of view what I got 394 is greater than is much greater than 206. Therefore even that minimum shear reinforcement criteria is also not governing. What is only governing is just from detailing point of view, just 0.75 D, just 0.75 D means not greater than 206 is only governing. Therefore now let us say let us provide the 8 mm dia 2 legged stirrups may be at 200 mm center to center, right? Now I'll show like this, right? I'll just provide like this, right? Therefore that is how at the support either you say 4 10 mm dia rods or the top rods the 3 12 mm dia rods just now we have seen, right? Even this design we have seen just now, right? 8 mm dia 2 legged stirrups at 200 mm center to center, this stirrups design, student, right? At this support, right? Now likewise now we'll see what is the design of the positive reinforcement, or the positive reinforcement means subjected to positive flexure, right? Right? Now let us see this design at a bigger page, right? Therefore now I do have the design. I'll just initiate, just have completed the design at the support. Now I'll initiate the design for positive bending moment, right? for sagging bending moment. Positive is called sagging, whereas negative is called at the supports hogging bending moment, right? At mid span, right? We have noted that the positive bending moment is 16.3 like this, right? 16.3 from this codal specification as well as from this manual calculation also, from this manual calculation. Therefore, now I'll substitute what is the area of the steel required. Therefore, upon substitution, how I explained elaborately in the previous subheading student. Therefore, if I substitute now, I get approximately 130 mm square, whereas from the STAAD I'm getting 122. That already indicated, right? Let me go to this STAAD student, right? I'll go to this right, this page, right? Therefore, I'm getting a positive steel as 122 in beam number 2, right, at the bottom, right? Therefore, I just noted down that, therefore, I require 129 from manual calculation, whereas 122. Almost there is a small error, hardly some 7 mm square less from the STAAD. I can ignore that. Therefore, use 212 mm dia bars, because 112 mm will furnish 113. Therefore, 129 will be 113. It is 1 point odd value. Say next integer is equal to 212. That is how the design for the sagging bending moment, right? Sagging bending moment. Therefore, now I will provide like this. Provide 2, not 10 mm student, right? We provide 2 12 mm dia bars, right? 2 12 mm dia bars as the positive bending moment at the bottom steel, right? Bottom steel. Whereas the hogging bending moment is provided at the support at the top, right? Whereas the sagging bending moment, for the sagging bending moment, the steel is provided, the tension is there in at the bottom, right? This is how the compression, the tension is at the bottom. Therefore, tension should be provided at the bottom, which is 2 12 mm dia bars, as shown in this section 1.1, right? Now, once I complete this like this, now you can even do. I think I will not go through that, right? Even you can take a section 2.2 where the shear force as well as bending moments are changing. There you can check the design, right? Check the design. But however, in any case, the number of rods should not be less than 2 12 mm dia bars as a negative steel, as well as the 2 12 mm dia bars in the as a positive steel, positive flexural steel, as well as now as you move away from the support, the shear reinforcement may be increased to a maximum value of 0.75D to 300 mm. Therefore, now I'll provide 8 mm dia 2 leg stirrups at a spacing of 300 mm, right? Like that, even you can see at the mid span of this curved support, right? Curved beam. There also you can see I'll provide at section 3.3 212 top, 212 bottom steel, as well as the shear reinforcement as 8 mm dia 2 leg stirrups at 300 mm center to center, right? That is all the detailing, right? This is for the flexure only. But however, this beam is also subjected to torsion like this, right? Torsion, right? Therefore, if it is subjected to torsion, then how? Let us check whether the provided design is okay or not, right? Therefore, you already noted down what is the torsion from manual calculation or as per that IS 4995 coefficients, right? Therefore, it worked out 4.909 kN as well as the shear force is 26.64. Therefore, as per this IS 456 class 41.3.1 from page number 75. Let me just move that page number 75 student, right? Page number 75. I'm just there in the page number 75, right? Shear and torsion, subjected to shear and torsion, equivalent shear VE is given by this formula. V is equal to VU plus 1.6 TU by B, as well as now the code says that if tau E does not exceed tau C, as given that table 19, the minimum shear reinforcement should be provided, whereas if tau E exceeds the tau C as given the table 19, both longitudinal as well as transverse reinforcement should be provided, right? And coming to the of how the longitudinal reinforcement should be provided is that now code says that this longitudinal reinforcement should be designed to resist an equivalent bending moment of ME1 given by MU plus M1, where MU M1 is given by TU multiplied by 1 plus D by B 1.7, whereas the TU is the torsional moment and D is the overall depth and B is the breadth of the beam. However, if the numeric value of this M1 just we have obtained is exceeding the numeric value of MU, ultimate movement, then the longitudinal reinforcement shall be provided. Longitudinal reinforcement shall be provided on the flexural compression zone also, in addition to the tension zone, not to to withstand an equivalent bending moment of ME2, given by this equation. ME2 is equal to M1 minus MU. The difference of this M1 minus MU, right, which is equal to ME2. That is what called the compression reinforcement bending moment, right? And the transverse reinforcement, two-legged closed stirrups should be provided at the corners of the longitudinal bars, given by this formula: ASV is equal to TU SV divided by B1 D1 0.87 Fi plus VU SV divided by 2.5 D1 0.87 Fi. But however, the transverse reinforcement shall not be less than, given by this formula, tau VE minus tau C multiplied by B SV divided by 0.87 Fi. What is that? B1 is the center-to-center distance between the corner bars in the direction of the width, and D1 is the center-to-center distance between the corner bars right, in the depth direction, and tau V is the equivalent shear stress and tau C is the design shear strength as per the table 19, right? Therefore, once I examine this class 41.3 student, therefore now I'll move to quickly. I've just revisited that codal specification at a quicker pace, or even you can alternatively go to SP6 class 4 page number 176, right? Now let me go to that SP6 page number 176 student, right? I'll go to that quickly, right? Subject to shear and torsion. Yes, this is there. I'm there in shear and torsion. The same are reiterated here, right? How that design shear stress is given by this formula, right? Shear strength is given by this formula, and tau V is equal to V divided by BD subjected to torsion, and this is the table for maximum shear stress. Just now we have seen for M25 3.1, and this also we have seen, but now subjected to shear and torsion. Therefore, now let us see subjected to torsion. This is example problem 11. You can see, right, 11, where it is giving that same formula: V is equal to V plus 1.6 TU by B. Therefore, now I'll calculate using this formula. Therefore, if I calculate that, I'll get nominal shear stress. The equivalent shear given by this VU plus 1.6 TU by B, whereas VU is equal to 26.64. 1.6 multiplied by TU is equal to 4.909 kilonewton. That divided by B, 230. Therefore, all the inputs are in terms of Newton mm. Therefore, now I'll get so many newtons. If I divide with 10 to the power 3, now I'll get 60.78 kilonewton as against actual shear stress at that location is equal to 26.6, right? Now, therefore, 60.78 minus 26.64. Therefore, there is an increase of 34.14 as against the base value of 26.64. Therefore, 26.64, almost there is an increase of 128%. 128% increase in the shear due to torsion. This much of small torsion of 4.9. There is an increment of 128. That indicates the effect of the torsion in the curved beams or ring girders in the water tanks, or that of the engine tank, or that of the deep bin ring girder beams, right? Therefore, we cannot neglect the torsion. Almost 128% increase cannot be neglected. Therefore, this formula will take care of that increase in shear stress. Therefore, with this shear, now I'll calculate what is the equivalent shear stress. Tau V is equal to VE, where VE is equal to 60.78 divided by BD. I know what is BD. Therefore, now it works out, say, 0.96 Newton per mm square. But however, this is much less than the 3.1 tau C maximum. Design shear stress is equal to 3.1. Therefore, okay. But now what is the tau C? Now we already provided the percentage of the steel. Even we got the design shear stress was just 0.49. Therefore, this nominal shear stress is much greater than that of the tau c. Hence, I need to design the design for the shear. Design for the shear. That is what the indication, right? That is what the indication, right? Now next one is I'll come to that, right? Now next one is that of the torsion, right? What is that? Torsion moment MT, right? Torsion moment MT as per this class 41.4.2 just now we have seen, or as per this SP 1980, which is the design aids for this IS 456 as per this class 4 page number 176 just now we have seen, right? That is MT is equal to TU is equal to 4.909 multiplied by 1 plus D by B, 300 divided by 230 divided by 1.7. Now it works out 6.65. Whereas now let us see this base value was 4.91, whereas now that value is increased to 6.65, means there is an increment of 1.74 kilonewton as against the base value of 4.91. Therefore, almost there is an increment by 35%. There is an increment in the torsion by equivalent torsion by 35%, student. Therefore, 35% increase in the torsion cannot be neglected. Therefore, I cannot neglect that value. Therefore, now my design moment is equal to this 6.65 kilonewton meter, right? Therefore, now what is that steel required? Right? Whereas now I'll go to how much of the moment of resistance of this section, right? We already designed the section to resist at the support at the midspan 16.3, whereas even at the support we have designed for 31.67. Therefore, mu is much greater than, just wait a moment, right? Mu is much greater than this mu what now we are getting 6.65. Therefore, whatever the design we have done is sufficient. Or let me check for 6.65 how much of steel is required. Therefore, as per this formula, 0.5 FCK divided by Fi 1 minus square root of 1 minus 4.6 mu divided by FCK BD square multiplied by BD. I just require 47.05 area of the steel only, but that AST minimum is equal to, as per that formula, 97. But this is to resist this much of bending moment. But however, the section is already designed for a negative bending moment of 31.67, where we have provided already 312 mm dia bars, whereas I require only 265, but provided is equal to 339 mm square. Therefore, my design for torsion is not that critical, but only design for negative bending moment is only critical. Therefore, once I get that, even now, just now we have seen that I require the design for the now from this, what now I can conclude that even I don't require any design for flexure in compression. As per this, I don't require any design for flexure as per the this numeric values, because here this 6.65 is much less than that moment of resistance of that section, right? Therefore, I don't require any compression steel, but nevertheless we need to provide at least 2 12 mm dia bars in the compression zone, right? Now that we already seen, right? Now once I do that, now let us see even the next one is check for the shear. Just now we have seen that the nominal shear stress is exceeding that of the design shear stress, which is 0.49. Therefore, I need to design the section. Therefore, I am just providing same. We already done that, right? 2 mm dia, 8 mm dia, 2 length vertical stirrups, right? They will give right, using this formula as per IS 456. Just now we have seen class 41.4.3 page number 75. 75, right? Therefore I do have this formula. Let me just revisit this formula, student, right? This is how that formula, ASV transverse reinforcement is given by this. ASV is equal to TU SV divided by B1 D1 0.87 Fi plus VU SV divided by 2.5 D1 0.87 Fi, right? However, this should not be less than tau V minus tau C multiplied by BSV divided by 0.87 Fi, right? Therefore, if I calculate using this, now I am getting that spacing, right? I am getting approximately 1305 mm. But however, that minimum shear reinforcement criteria, just now we have seen that ASV by BSV should be greater than or equal to 0.4 divided by 0.87. Therefore, from that I got 394. Therefore, still here this torsion is not that critical. Therefore, that even minimum shear reinforcement criteria, from that I need to provide 394. But now let me check from this other criteria point of view. Even the code says that this ASV shall not be less than tau V minus tau C BSV divided by 0.87 Fi. Therefore, as per this, now what is that? Now I am getting even the spacing as per that I am getting 359. Whereas from the regular calculation I got 1305. From that minimum point of view 359, but nevertheless 359 will govern, right, compared to that of the minimum shear reinforcement point of view 394, right, 394. But now I got even this 359. Therefore 359 will govern the design. 359 will govern the design from the combined shear and torsion, not that of the minimum shear reinforcement. 394 will not govern the design. Please make a note, student, right? I hope you are understanding these discussions. Therefore, I should not have more than 359, but nevertheless this will not govern the design. But however, just now we have seen even the code safeguards the designs like this, that saying that the spacing of these vertical strips should not be more than 0.75 D. Therefore, 206.25 or 300 mm. 206 is not more than 300 mm. Therefore, 206. Therefore, now here also I'll say that no, even this is not governing, right? Even 359.19 is not governing. Therefore, now I'll say that okay, provide the 8 mm dia 2-legged vertical strips at a spacing of 200 mm at the supports like this. Whereas as you move to the center of the span of this curved span like this, right, at this, right, you can increase to 300 mm. Whereas at the support 200 mm slowly increase to 300 mm, right, 300 mm, right. That is how the design, right, that is how we will increase from 200 mm to slowly to the mid span 8 mm dia 2-legged vertical stirrups to 300 mm stirrups, right, 300 mm stirrups as shown in the figure, right. That is how we have seen this you already seen, student, right. These are the loading we already examined, right. This is how the variation of the shear force, right, variation of the shear force as well as that of the variation of the bending moment, right. Variation of the bending moment, this is the variation of the shear force. Previously it was the variation of the bending moment, right. That is all, right. Maximum 33.462 is maximum of 33.46. Variation of the shear force, negative bending moment to positive bending moment, right. And the shear force variation diagram, SFD diagram, right. This also we have seen minus 45 to plus 45 and minus 45 to plus 45. That is how we have examined. Even this also we have seen the other variation, the other variations we already examined, right. Now I hope, student, now we have done the design of this circular curved beam subjected to a UDL load, right, with modeling assuming as a straight beam, whereas if I model this using a curved beam, like this, right, I am there in this, right, all these are the straight lines, right. Whereas if I just model this as a straight instead of straight beam, if I model this as a curved beam, what will happen, right? Now let me revisit to that that problem, student, right? Therefore I am there in that, right, the second modeling. Therefore I am having now this modeling, right? As you can see that this part is only just shown as one curved single span beam, right? Like that I do have the other part, right? The other part, second part, right? Second part, third part, so on and so forth, right? Second part, right? Or the third span, right? Like this, right? The third span between two column supports, right? And that of the fourth span, right? That is how this curved beam, right? This we already designed, but now I'm modeling this using the geometry, the beams curved beam. Previously I have modeled that using just a straight line. Now I am modeling that using a curved beam option, student. Just make a note of, right? And there in geometry page, add beam, add curved beam. Therefore I have just added, I have created 4 nodes, right? These are the nodes, right? Let me go to the setup, right? These are just explain this, right? I have defined the geometry. I have 4 nodes, right? That first node, that first node, just a moment, right? These are my node numbers, right? Node 1, 2, 3, 4, right? My first node is there at x is equal to 2.5, y is equal to 0, and z is equal to 0, and the second node is equal to 0, 0, minus 2.53 is the third node is equal to minus 2.500, and fourth node is equal to 0, 0, 2.5. Therefore, at these nodes I have just created the column supports, at which I have just connecting these. I have assigned 4 curved beams, like this, right? 4 curved beams, right? Therefore, if I now remaining part is same, right? I'll assign the same column properties, and even I'll assign the same support condition. All the 4 supports are the fixed support, and I'll assign even the loading. I'll assign the same loading. There is no change in loading, right? Sulfate I have not changed. Even that UDL 14 kN per meter UDL due to live load. Even the combination load 1.5 multiplied by this one, right? All these are same. Material is also same. Concrete I have not changed, right? Even now I have done analysis as well as I have gone for the design. As per IS 456, right? Therefore IS 456, right? Therefore using that IS 456, right? Using the same FCK 25 main steel 550, secondary steel 415, right? Torsion 0 means consider torsion and design all these beams, 4 beams, and take concrete quantity. Therefore, doing this, now I am having the output. Now let me just run analysis, student, right? Just in 1 second I got the outputs. Now you can see there is a advantage of using this software. Now let me check what are the beams that are failing. Now it is showing that yes, it is giving warning that the section is failing while detailing at the support, right? Like that many warnings are seen, right? Now even if I check, even find next, right? All these are giving that no, right? That is how. However, the shear force at that support is equal to 46.31, right? Even you can see the other at other locations, right? Even what is the shear force variation, right? And even the torsion you can see 2.2, right? Therefore, once I note this, right? Now I'll go to that of the post processing page, student, right? And then the post processing page. Now for this, now I'll see what are the graphs for these beams, right? Now from this page, if I go to this graph, now code says this STAAD says that graphs for the curved beams are not available. There is a disadvantage. Therefore, I have not shown the outputs using this modeling this beam as a curved beam. Indeed, I have modeled that using straight beams so that I don't have any difficulty in noting down the values in the form of the graphs. But however, there is no such restriction from the forces point of view. Yes, now the forces are available, right? At the support 1, the shear force is equal to 46. Now let me highlight this page, student, right? This is how at the support 1 I do have the maximum shear force of 46.314, and the torsion is 2.217, and the maximum support moment is equal to 33.84. Like that, you can see at other locations also the same values indicated, right? These are the design forces. The design forces are just noted down, right? Now let me just go revisit, right, to that of the change in outputs, right? That are already shown compared to that of the manual calculation as well as that of when I have modeled that using a state beam. That I already told that using manual calculation I got negative bending moment as 31.67, whereas if I modeled that curved beam using a straight beam, I got the output, I got the result as a minus 33.66, which is 6% more. Whereas if I am just modeling that as a curved beam, now I am getting 33.85 from the table. Therefore, either 33.85 or minus 33.66. Therefore, whether the graph variation is shown or not, the STAAD is not giving any erroneous result. It is not giving any. It is in conformity with that of whether you model this as a straight beam or that of the curved beam. There is no error. It is in line with that of the results what we obtained with that of the straight beam. Therefore, there is no much change in output, right? Even similarly, now it cannot give the maximum bending moment at the midspan, that you can see, right? Now let us see what is the torsion, right? When we have modeled using that like a straight beam, the torsion value from manual calculation it was 4.91, whereas from STAAD modeling it as a straight beam it was 4.91, whereas now modeling this as a curved beam, now I am getting 2.22 compared to that of the previous one 3.41. almost here 1.21 is error. Therefore 1.21 compared to that of 3. This one is almost say here roughly 30% error. That is how the change in analysis outputs when modeling this as a curved beam. I hope student you understood the discussions what we had in today's class, right? In today's class we have discussed the analysis as well as the designs of a curved beam subjected to the external live load, right? Now if you really loved these discussions, right, don't forget to subscribe to our YouTube channel and like, comment, share and turn on your notifications to our YouTube channel as well as that of the different videos, right? We'll meet in the next class with another discussion. Till then, bye bye students.